Hello guys, welcome to the Tootin' Bros. Today we're going to be looking at electrophilic aromatic substitution with a halogen electrophile, otherwise known as halogenation. So, electrophilic aromatic substitution with a halogen starts off with an aromatic, like benzene, reacting with Br2 or Cl2. The reason it doesn't F2 or I2, the reason that these two halogens do not react is because fluorine is too reactive, it's too unstable, and iodine is too unreactive and would result in low yield of products. So this reaction is done with Br2 or Cl2. And their end product would be the original aromatic compound with a halogen attached to it. So in this reaction, we'll use Br bromine for this example, but it's the same exact thing with chlorine. In this reaction, the alkene on the benzene or the alkene on the aromatic is the nucleophile, and the halogen is the electrophile. So the reason that the halogen is the electrophile, even though it is a nonpolar compound, is because when this bromine molecule gets closer to the alkene, it creates a temporary dipole moment, where the bromine closer to the alkene gets a partial positive charge, and the halogen atom farther away gets a partial negative charge. So this creates a temporary dipole moment that makes this molecule an electrophile. But these two molecules together would not react because benzene is aromatic and it doesn't want to lose aromaticity, because aromatic compounds are the most stable type of compounds compared to non-aromatics and anti-aromatics. So they want to stay aromatic. So what this would need is a catalyst to drive this reaction forward, to let this reaction happen. And the catalyst used for aromatic electrophilic substitution are Lewis acid catalysts. And Lewis acid catalysts are metals bonded to a halogen, so AlBr3, AlCl3, FeBr3, FeCl3, etc. So there's multiple other Lewis acid catalysts, but these are just some to name a few. And when you're doing halogenation, you want to use the Lewis acid catalyst where the halogen is the same as the halogen you're substituting, because you would be doing this in a reaction flask and you don't want to have two different types of halogens. You don't want to have bromine and chlorine in the same reaction flask, because you won't get 100% of the product that you want, which would make this reaction unproductive. It would render it pointless. So this is how the reaction would look. You have benzene reacting with, again we'll use Br2, but it's the exact same for chlorine, and we'll have AlBr3. So this is what you see if you have like a problem that involves halogenation, and for this example we're going to use simple benzene. This can be done with other aromatic compounds. It could be done with benzene with a substituent, but if it's done with benzene with a substituent, you would have to take into activators and deactivators, which will not be covered in this video. So we're just going to be looking at benzene. So when you're starting off with the mechanism for this reaction, we're actually not going to start off with benzene. We're going to start off with our other reactant, with our catalyst, because benzene is aromatic. Again, it's not going to want to start a reaction. Something else will have to start the reaction. So what starts the reaction? So we have bromine, and then we have AlBr3. So bromine, so a lone pair on one of the bromine molecules will attack the metal of our Lewis acid catalyst, and this will create a reversible reaction. It will create a bond between both molecules, and this bond is not very stable because our bromine right here has more bonds than it wants to, so it's going to have a positive charge. If you wanted to calculate the formal charge for this bromine, you would find it to be +1. And then this aluminum, or the metal, whatever metal, will have a minus charge. It has more bonds than it wants to, and metals want to lose electrons to make bonds, not gain them. So this is what our molecule looks like, and now we have our electrophile. So this is the electrophile of a reaction. And then now this is where benzene comes in. So we just created a suitable electrophile for our reaction. Okay, so now benzene will be more willing to react. So benzene will have a nucleophilic attack on the outermost bromine, or at the outermost halogen, the one without the positive charge. That's going to push the electrons. It's going to break that bond, push the electrons to the bromine with the positive charge. Okay? And this is again a reversible reaction. And then now we're going to have this molecule. So this bromine no longer has a positive charge. It only has one bond, which is what it wants. But the aluminum still has more bonds than it wants, so it's still negative. And this right here is going to be our base. Okay? And then I'll go to the next page for here, because we're running out of space. But now we have bonded our halogen to our aromatic, but it is no longer aromatic. So going from here to here, it's very reversible. It's gonna favor going in this direction more because it's losing aromaticity. When it does this nucleophilic attack right here, it's losing aromaticity, and it does not want that. So it leans very forward in this to the left. But now we have a non-aromatic, and we have a carbocation right here, because we broke a double bond. So we still have a hydrogen here, hydrogen here, hydrogen here, hydrogen here, hydrogen here, and here as well. But because there's no double bond here, the carbon only has 3 bonds. It's a carbocation. And from here, we can create our sigma complex. So what a sigma complex is, it's just a collection of resonance structures. between the intermediate carbocation. So we can move this double bond right here. That creates another resonance. We'll not draw in the hydrogens this time. But now our positive charge is here. So now this double bond can move there. And it creates another resonance structure. Double bond is now on the left. This double bond is still there. Now the positive charge is on the top. So when you're doing electrophilic substitution with aromatics, you're going to have at least 3 resonance structures in your sigma complex. So this is the sigma complex. You're going to have at least 3 resonance structures. When you get to more complicated problems, this can increase, but generally you're going to have at least 3. So now is where our base that we created right here, this is where our base comes in. So we have our base, Br Al minus, still has that negative charge from earlier. And what's going to happen is, remember, we're going to be focusing on this hydrogen that is attached to the same carbon as the substituent that we added. So what's going to happen is the bond will attack the hydrogen. The electrons in this bond will attack the hydrogen, and then the electrons in the bond between carbon and hydrogen will go here and create a double bond. So this bond is broken, this bond is broken right here. The bond between Br and Al, and the bond between hydrogen and carbon, and a new alkene bond, double bond, is created. So now we get our product. So we get we get the aromatic back, Br, but also because we had a proton transfer right here and a breaking of the double bond, we get hydrobromic acid, and we get the regeneration of our catalyst. So that's why it's a catalyst, because we started off with AlBr3 and we end off with AlBr3. It is not used in the reaction. And this part of the reaction is also irreversible because we're gaining aromaticity. So we went from non-aromatic to an aromatic. So the reaction is not going to want to go back that way. It's only going to want to go this way. So those are our 3 products. And this benzene with the bromine is our main product. That's the one we actually care about. This is just a byproduct, and this is just the catalyst. So this is what we actually care about. If you want to look at any other topics, comment them, and if you want to go over other electrophilic aromatic substitutions, we'll be covering them in the next few days.